Hello there, and a very quiet, warm welcome to Astro Dreams. I am truly, deeply glad you have found your way here tonight to this quiet corner of the cosmos. However your day has been, whatever thoughts are still swirling in your mind, you can let them all go now. There is nothing you need to do, nothing you need to solve, nothing you need to remember. Just find a comfortable position, let your breathing slow, and allow your body to grow heavy, as if gravity itself is holding you in a gentle, secure embrace, pulling you softly into rest. Tonight, we are going to take a long, slow, and peaceful journey to the most serene and mysterious places in the entire cosmos. We are going to explore black holes, but we will not approach them with fear or urgency. Instead, we will drift near them with a sense of quiet wonder and profound peace. We will contemplate their immense, silent gravity and listen to the stories they tell about space, time, and the very nature of reality. Let the deep, dark tranquility of these cosmic wonders lull your mind into a state of perfect, restful calm. Let each fact be a soft step deeper into relaxation, a gentle wave washing over your conscious mind, carrying you towards sleep. Some of what you hear tonight may surprise you, or spark a gentle, sleepy curiosity as you drift away. And just before we begin, if these calm, cosmic explorations help you unwind and find a quiet way to end your day, consider liking this video and subscribing to the Astro Dreams channel. It helps other tired souls find their way here, to a place of peace under the stars, a community of sleepy dreamers drifting through the universe together. Now, let your mind grow quiet, let your awareness soften, like a cloud dissolving in a vast, calm sky. Let's begin our gentle, slow journey into the heart of darkness, into the silent, peaceful realm of black holes. There is no rush. We have all the time in the universe. A black hole is not a hole in the way we normally think of one. It is not a void, not an emptiness, not a pit. It is a place in space where matter has been compressed into an incredibly tiny, dense point. A place where gravity has become so strong, so deep, so profound, that nothing, not even light, can escape its gentle, relentless pull. It is a cosmic presence. A silent giant sleeping in the dark, a monument to the power of gravity. The idea of a black hole was first imagined not with complex telescopes, but with quiet, profound thought. An English clergyman and natural philosopher named John Michell, back in the 18th century, pondered the nature of light and gravity. He sat and he thought, and he pictured what he called dark stars. Stars so massive and dense that their gravity would not allow light to shine free. It was a speculative whisper, a quiet thought experiment, a seed of an idea planted long before we had the technological means to see such things. It was a prediction born from pure reason. And later, the great Albert Einstein, with his theory of general relativity, gave us the mathematics to understand how gravity could warp space and time so severely. He showed that mass tells space-time how to curve, and that curved space-time tells mass how to move. And within his equations, the potential for black holes was hidden, waiting to be discovered. Karl Schwarzschild found a solution to these equations while serving on the front lines in World War I, a solution that described a point of infinite density. The idea was born from war, but it described a perfect, silent peace. Black holes begin their lives in the quiet, graceful, and yet violent end of the most massive stars. A star is a balancing act, a constant struggle between the outward push of nuclear fusion in its core and the inward, relentless pull of its own gravity. For millions, even billions of years, this balance holds. But when a giant star, many times larger than our Sun, has finally burned through its nuclear fuel, a beautiful and final transformation occurs. The fusion stops, the outward push vanishes, and in that moment, gravity wins. The star's core, with no support left, begins to collapse. It falls inward at an incredible speed. The outer layers of the star initially rush inward as well, but then they hit the rebounding core and explode outward in one of the most energetic events in the universe, a supernova. For a few weeks, that one star can outshine its entire galaxy. It is a glorious, fiery farewell. But the core's story is not over. If the core is more than about 3 times the mass of our Sun, no known force in the universe can stop its collapse. Not the pressure of electrons, not the pressure of neutrons. Nothing. It collapses down, 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 crushing itself into a point of near infinite density, and in that final, silent surrender to gravity, a black hole is born. From the ashes of a stellar explosion comes the ultimate silence. The boundary around a black hole is called the event horizon. It is not a physical surface you could touch or see or land on. It is a mathematical boundary, a point of no return, a silent, invisible threshold in the fabric of space itself. Once something, a particle of dust, a photon of light, a spaceship, a star, crosses this boundary, it cannot come back. It is gone from our universe forever. But the crossing itself would be smooth, a quiet, seamless fall into the dark. There is no wall, no barrier, no line painted in space. It is a transition as smooth as floating from warm water into cool. From the outside, the event horizon appears as a perfect black sphere, a dark marble against the backdrop of a million shimmering stars. It is the blackest black imaginable, because no light, no information can ever come back out to reach your eyes. At the very centre of a black hole, according to our current theories, lies the singularity, a place where all the mass is crushed into a point of zero volume and infinite density. Here, our understanding of physics simply fades away. The laws of space and time as we know them cease to have any meaning. The concepts of here and there, of before and after, break down completely. It is the ultimate mystery, a quiet question mark at the very heart of the darkness, a place where science meets its limits and must whisper, "We do not know." Black holes come in different sizes, like quiet families of cosmic objects, each with its own story. There are stellar mass black holes, weighing just a few times the mass of our Sun. These are the remnants of those giant stars we just spoke of. They are scattered throughout galaxies like quiet ghosts. Then there are supermassive black holes, millions or even billions of times the mass of the Sun, living in the centres of nearly every galaxy, including our own. How they grew so large is still a mystery. Did they form from the direct collapse of immense gas clouds in the early universe? Or did they start as smaller black holes and grow over billions of years by merging and consuming gas? We are still piecing together their origin story. And there may even be primordial black holes, a fascinating hypothetical class. These would not be formed from dying stars, but from the extreme densities and pressures present in the very first searing moments after the Big Bang. If they exist, they could be any size, from a microscopic speck to a mass larger than a mountain. They are cosmic relics, possibly floating unseen among us. The first black hole ever confidently identified is a stellar mass black hole known as Cygnus X1. It is located right here in our own Milky Way galaxy, about 6,000 light-years away. It is locked in a slow, intimate, gravitational dance with a brilliant blue supergiant star called HDE 226868. The black hole's immense gravity gently pulls a stream of material from its companion star. This material doesn't fall straight in. Instead, it forms a vast, swirling disk around the black hole, called an accretion disk. As the gas in this disk spirals inward, it rubs against itself, creating immense friction. This friction heats the gas to temperatures of millions of degrees, causing it to glow not with visible light, but with a soft, persistent whisper of X-rays. It is this X-ray signature that allowed astronomers to find it, a high-energy lullaby in the cosmic night, a beacon of invisible light. The supermassive black hole at the center of our own Milky Way galaxy is named Sagittarius A, often abbreviated as SDR-A. It has a mass of about 4 million times that of our Sun. Think of that for a moment. 4 million suns. Yet, all that immense, almost unimaginable mass is contained within a region of space smaller than the orbit of Mercury. The density is staggering. For now, SCR-A times is quiet, dormant. It is not actively feeding on large amounts of gas, but its presence is undeniable, its influence absolute. For decades, astronomers have been tracking the orbits of stars very close to the galactic center. They have watched these stars, like S2 and S0-102, whip around an invisible point at speeds of thousands of kilometers per second, tracing elegant, looping orbits that clearly point to the presence of a supermassive, invisible object. It is a slow, silent, and relentless ballet, choreographed by gravity alone. We cannot see black holes directly, for they emit no light of their own. They are the quietest objects in the universe, the ultimate secret keepers. Instead, we are cosmic detectives, finding them by watching how they interact with the space and matter around them. We look for the clues they leave behind. We see stars orbiting an invisible point, tracing elegant ellipses around nothingness. We see those bright, hot accretion disks of gas and dust glowing with intense heat as they spiral inexorably inward. We observe the jets of material that sometimes scream out from their poles. And now, most amazingly, we listen. We listen for the faint, rhythmic ripples in space-time they create when they move, and especially when they collide with one another. We have learned to hear the universe. If you were to fall towards a black hole, you would experience a strange and gentle effect known as spaghettification, or the noodle effect. It is a whimsical name for a profound process. The gravitational pull on your feet would be so much stronger than the pull on your head that your body would be stretched lengthwise. At the same time, the gravitational pull from the sides would compress you inward. You would be stretched and squeezed simultaneously. It sounds dramatic, even terrifying, but in the vast, silent solitude of space, far from any help, it would be a slow, almost meditative process, a quiet unraveling. You would be transformed gently into a stream of atoms, all lining up to enter the event horizon, one after the other. You would become one with the flow. Time itself slows down near a black hole. This is not science fiction. It is a direct and beautiful consequence of Einstein's theory of general relativity, an effect called gravitational time dilation. Gravity warps time. The stronger the gravity, the slower time passes. If you could take a spaceship and hover just outside the event horizon, with powerful rockets fighting the immense pull, you would witness a strange sight. Looking outwards, you would see the universe outside speed up. Stars would flare and die in fast forward. Galaxies would swirl and merge in a silent, accelerated film. Eons would pass in what felt like minutes for you. But for you, inside your ship, time would flow normally, second by patient second. It is a gentle bending of the cosmic clock, a quiet stretching of moments. From the perspective of someone far away, safely watching you fall into a black hole through a powerful telescope, you would appear to slow down. As you approach the event horizon, your image would redden and dim. Your clock would seem to tick slower and slower. You would become frozen in time at the very edge of the event horizon. Your final moment stretched across millennia. Your light fading slowly into nothingness. You would never quite seem to cross, becoming a permanent ghostly image etched onto the threshold of darkness, a fading photograph from the edge of forever. It is a common misconception that black holes are cosmic vacuum cleaners, randomly sucking everything into their grasp. This is not true. Their gravity is simply very strong, but only very close by. Their gravity follows the same inverse square law as any other object. If you are far away, the pull is weak. To illustrate this, imagine a thought experiment. If our sun were, by some magic, instantly replaced by a black hole of the exact same mass, nothing about the solar system's orbits would change. The Earth and all the planets would continue to circle it in complete and utter darkness, held by the same familiar gravitational pull. The solar system would become a silent, dark clockwork, ticking away in the void, illuminated only by the distant stars. The planets would not be sucked in. They would follow their same paths in perpetual night. Black holes can spin. Most things in the universe spin: planets, stars, galaxies. When a star collapses to form a black hole, it conserves its angular momentum. Just like a figure skater who pulls their arms in spins faster, the collapsing core of the star spins faster and faster. A spinning black hole, known to physicists as a Kerr black hole, does something remarkable. It drags the very fabric of space and time around with it, an effect known as frame dragging. It creates a region outside the event horizon called the ergosphere, which is shaped like a flattened sphere. Within the ergosphere, nothing can stand still. Space itself is set into a slow, swirling motion, like a cosmic whirlpool. You would be forced to move, to rotate with the black hole, just by being there. The accretion disk around a black hole is a place of beautiful, violent calm. It is a vast, flat river of gas and dust, orbiting the black hole at tremendous speeds, often a significant fraction of the speed of light. The material in the inner part of the disk orbits much faster than the material in the outer part. This difference in speed creates immense friction and shear forces. This friction heats the gas to temperatures of millions of degrees. It becomes a plasma so hot that it glows not with the visible light we see, but with X-rays and other forms of high-energy radiation. This disk is the brightest part of a black hole system, a luminous, flat whirlpool of doomed matter, shining softly against the infinite dark, a final, brilliant dance before the great silence. Sometimes, from the poles of a black hole's accretion disk, colossal jets of material are fired out into space. These are not made of light, but of charged particles, electrons and protons that have been accelerated by the black hole's immense magnetic fields to nearly the speed of light. These jets can stretch for thousands, even millions of light years, far beyond the boundaries of their host galaxy. They are shaped and focused by intense magnetic fields, carving through the interstellar and intergalactic medium like silent cosmic blowtorches. They are a testament to the powerful, hidden engine at the black hole's core, a signal of immense energy released in a perfectly straight, narrow line across the cosmos. When two black holes find themselves orbiting one another, they perform the most silent, the most profound dance in the universe. They are typically the end result of binary star systems, where both stars were massive enough to become black holes. As they orbit, they lose energy. But this energy is not lost as light or heat. It is lost as gravitational waves. These are ripples in the fabric of space-time itself, predicted by Einstein over a century ago. Think of space-time as a taut rubber sheet. The orbiting black holes are like two bowling balls spinning around each other on that sheet, creating ripples that travel outward at the speed of light. As the dance continues, over millions of years, they spiral closer and closer together, and these gravitational waves grow stronger. The ripples become larger. The pitch of the wave increases. And then, finally, in a final, breathtaking moment, the two black holes merge into one. The event sends a final, powerful chirp of gravitational waves out across the universe, a silent song of unification, a brief storm in the fabric of reality. The first direct detection of these gravitational waves came on the 14th of September 2015 from an observatory called LIGO, the Laser Interferometer Gravitational Wave Observatory. The signal, named GW150914, was from the merger of two black holes about 1.3 billion light-years away. One was about 36 times the mass of the Sun, the other 29 times. They merged into a final black hole of about 62 solar masses. The missing 3 solar masses of energy were converted into the gravitational waves that LIGO detected. It was a monumental moment for science. It confirmed a major prediction of Einstein's theory and opened a brand new window onto the cosmos. We are no longer just stargazers. We are now universe listeners, hearing the quiet collisions of things we cannot see, a symphony played on the strings of space-time. When black holes merge, the new single black hole has a mass that is slightly less than the sum of the two original black holes. This is because of Einstein's most famous equation, E equals mc squared. Mass and energy are equivalent. The missing mass was converted into pure energy, radiated away as those very gravitational waves. In that final, fleeting moment of merger, an amount of energy greater than the combined light of every star in the observable universe was released, all in the form of these silent, invisible ripples in space. It was the most powerful astronomical event ever recorded by humanity, and it was completely dark, completely silent in the traditional sense, a testament to the hidden energies of the cosmos. Stephen Hawking made a startling discovery in 1974. He found that black holes are not perfectly, eternally black. Due to strange and subtle quantum effects near the event horizon, they slowly evaporate, emitting a faint glow of particles. This is now known as Hawking radiation.
Here is how it works in a simplified way. According to quantum mechanics, empty space is not truly empty. It is a seething foam of virtual particles, particle and antiparticle pairs, constantly popping into existence and then annihilating each other. This happens everywhere, all the time. Now, if such a pair pops into existence right at the event horizon, a strange thing can happen. One particle falls into the black hole, while the other escapes into space. From the outside, it looks like the black hole has just emitted a particle. To conserve energy, the particle that fell in must have negative energy, which reduces the mass of the black hole. So, very slowly, the black hole loses mass. It evaporates. For a large, stellar, or supermassive black hole, this process is immeasurably slow, taking far, far longer than the current age of the universe. But for a very small, theoretical black hole, the evaporation would be rapid, ending in a final, bright flash of energy. Hawking radiation means that over trillions upon trillions of years, even black holes have a lifespan. They, too, eventually fade away into nothingness, returning their energy to the universe. A black hole, in its profound simplicity, has only three properties that we can measure from the outside: its mass, its electric charge, and its spin. This is known as the no-hair theorem. Hair here is a metaphor for all the other complicated details. It means that every single detail of the matter that fell in, what it was, whether it was a star made of hydrogen or a spaceship made of metal, where it came from, its history, its composition, is lost. Irretrievably lost. The black hole remembers only these three numbers: how heavy it is, how much it's spinning, and whether it's charged. It is the ultimate simplification, a cosmic erasure of all complexity. A black hole is the universe's way of forgetting. There appears to be a theoretical maximum size for a black hole, known as the ultramassive black hole. The largest known are the supermassive black holes in the hearts of the most massive galaxies, like the one in the galaxy Home 15A, which is estimated to be 40 billion times the mass of our Sun. But as the universe continues to expand and cool, and galaxies drift apart, the reservoirs of gas that feed these giants will become inaccessible. It is thought that black holes will eventually stop growing. They will become isolated, dark islands in an ever-expanding, ever-darkening, and cooling sea, shining only with the faint, slow glow of Hawking radiation. Black holes can also collide with neutron stars, the ultra-dense, city-sized cores left behind after a supernova. In these cataclysmic yet silent events, the neutron star is torn apart by the black hole's immense tidal forces before it ever crosses the event horizon. This destruction creates a spectacular, short-lived flash of light across the electromagnetic spectrum and a shower of heavy elements. The neutron star is ripped apart, and its material, rich in neutrons, undergoes rapid neutron capture, or the R process, forging heavy elements like gold, platinum, and uranium. These events are cosmic forges, seeding the cosmos with the very elements that make up our jewelry and our planets. Some galaxies, known as quasars or quasi-stellar radio sources, have incredibly bright, brilliant, point-like centers. This light is not from stars, but is powered by a supermassive black hole in a state of intense, voracious feeding. As vast amounts of gas and dust fall in, the accretion disk shines with the light of 1 trillion stars, outshining the entire galaxy of hundreds of billions of stars around it. A quasar is a black hole in its active, luminous youth, a beacon from the early universe when gas was more plentiful. They are the most persistently luminous objects in the cosmos. Our own Milky Way's black hole, Sagittarius A star, is quiet now. But astronomers have found evidence buried in the motions and compositions of gas clouds around it that it was active in the past, flaring up as a low-level quasar or active galactic nucleus millions of years ago. The enormous Fermi bubbles, giant ghostly structures of hot gas stretching 25,000 light-years above and below the galactic plane, are likely the fossil remnants of those ancient, powerful outbursts. They are a silent memory of a more violent youth, a time when our galaxy's heart burned brighter. Far from being destructive monsters, black holes are now understood to be essential, regulating parts of the cosmic ecosystem. They are not just endpoints, they are active participants in the life of a galaxy. The energy they release can govern the rate of star formation in their host galaxies. The jets and winds from a feeding black hole can heat the surrounding galactic gas, preventing it from cooling and collapsing into new stars. In this way, a black hole acts as a gentle cosmic thermostat, controlling the growth and evolution of its own galaxy. In the vast, sprawling scale of our galaxy, 100,000 light-years across, that is a next-door neighbor. But it is perfectly harmless, sleeping in the dark, its presence only known by the subtle, telltale wobble it imposes on its companion star. It is a silent companion in our galactic neighborhood. In April 2019, the world saw the first ever direct image of a black hole's shadow. It was the supermassive black hole at the heart of the galaxy, Messier 87, a giant elliptical galaxy 55 million light-years away. The black hole itself is 6.5 billion times the mass of our Sun. The image shows a brilliant, fiery, asymmetric ring of light, which is the photon sphere, the region where light orbits the black hole in unstable paths, and a dark central shadow. That shadow is about 2.5 times larger than the actual event horizon, because the black hole's gravity bends the light around it, creating a shadow of absence. It is a picture of pure gravity, a silent, stunning confirmation of our deepest theories about the nature of space and time. A dark pupil in a ring of fire. Taking that historic picture required a telescope of virtually impossible size. It was called the Event Horizon Telescope, or EHT. It was not a single instrument, but a synchronized network of 8 radio observatories spread across the globe, from the mountains of Hawaii to the peaks of the Andes to the frozen plains of Antarctica. Together, using a technique called very long baseline interferometry, they acted as one giant, Earth-sized virtual lens. The coordination was immense, requiring atomic clocks to synchronize the data collection. They observed for several nights in April 2017, and it took 2 years to process and piece together the data into the image we all saw. It was a monumental achievement of human collaboration and ingenuity, a quiet, persistent effort by hundreds of scientists from around the world to see the unseeable. The interior of a black hole is a place where our intuition fails completely. According to the classical theory of general relativity, once you cross the event horizon, all paths lead inward, toward the singularity. There is no going back, no turning around. Space becomes so warped that the future direction for every object, for every particle of light, points toward the center. Some theories suggest that inside, the roles of space and time may switch. What we perceive as the inevitable forward march of time towards the singularity might become a direction in space, like moving left or right. And what was a spatial dimension outside becomes a temporal one inside. It's a concept that is impossible to truly visualize, a gentle reminder that the universe is far stranger, far more wondrous than we can ever imagine. Our everyday experiences are a poor guide to the reality of the cosmos. Not every collapsing star becomes a black hole. The universe has other, quieter fates, other ends for stellar lives. Smaller stars like our sun will end their lives as white dwarfs. Medium-sized stars become neutron stars, city-sized spheres of unimaginable density where a teaspoon of material would weigh billions of tons. They are held up by neutron degeneracy pressure. It takes a truly massive star with a core more than about 3 times the mass of our sun to overcome even this pressure and create a black hole. It is a final, dramatic farewell reserved for the true giants of the stellar world, the behemoths, whose deaths create the ultimate silence. The theoretical density required to form a black hole is defined by its Schwarzschild radius, named after Karl Schwarzschild. For an object of any given mass, if you can compress it within this radius, it will become a black hole. The formula is simple. The Schwarzschild radius is 2 c squared, where g is the gravitational constant, m is the mass, and c is the speed of light. For the Earth, this radius is about 9 millimeters. That means crushing all of its mass, all its mountains, oceans, and continents, every city, every living thing, every memory, into a sphere less than a single inch across. For the Sun, the Schwarzschild radius is about 3 kilometers. It illustrates the incredible, silent power of gravity to warp space, turning an entire world or a brilliant star into a silent, dark marble. Black holes are often social creatures. They can exist in binary systems with other black holes, or with stars, or with neutron stars. Their gravitational dance can be stable for billions of years, a slow, patient waltz through the void. They are not necessarily lonely objects, but often exist in quiet partnerships. Their immense mutual gravity binding them together across the emptiness. Sometimes these partnerships end in a merger, a final embrace. Other times, they can last for the lifetime of the galaxy, a perfect The study of black holes has forced physicists to confront the single biggest problem in theoretical physics: the conflict between general relativity, which describes gravity and the very large, the fabric of space-time, and quantum mechanics, which describes the world of the very small, the world of probability and particles. The center of a black hole, the singularity, is precisely where these two magnificent, successful, and yet incompatible theories meet, disagree, and break down. General relativity predicts the singularity, but quantum mechanics abhors such infinities. To understand the singularity, we need a theory of quantum gravity, a way to marry these two pillars of physics. It is the final frontier of our understanding, a quiet, persistent mystery waiting to be solved, a puzzle at the heart of every black hole. Some speculative theories born in the pages of science fiction and the equations of theoretical physics suggest that black holes could be gateways. Perhaps they lead to other universes or are tunnels through space-time known as wormholes or Einstein-Rosen bridges. There is no physical evidence for this, and it likely violates the known laws of physics, particularly because wormholes would require exotic matter with negative energy density to stay open. But it remains a beautiful, peaceful, and captivating thought that a black hole is not an end, but a passage, a doorway to another reality, another time, or another universe entirely. A cosmic subway system connecting distant points. The energy efficiency of a black hole's accretion disk is, by cosmic standards, astoundingly high. Matter converting to energy through nuclear fusion, like in the core of a star, is only about 0.7% efficient. That is, but matter swirling down into a black hole through friction and the immense release of gravitational potential energy can be up to 40% efficient at converting mass into pure energy. It is one of the most powerful and efficient engines in the universe, and it runs on silence and gravity alone, converting mass into light and heat with breathtaking proficiency. There are no solid surfaces in a black hole system, nothing to crash into, no ground to hit. An astronaut falling in would encounter only the smooth, increasingly warped geometry of space. The fall would be seamless, a quiet, gliding journey inward, with no bump, no jar, no impact, no sound. Just the increasing gentle pull of the tidal forces, stretching and calming. It would be a silent, smooth descent into a geometry that curves infinitely, a journey into the heart of a mathematical truth, a fall without end into a point of infinite curvature. Black holes can, over immense timescales, lose their spin. Through various complex processes, like the Blandford-Znagic mechanism, where energy is magnetically extracted from the black hole's rotation, a spinning black hole can gradually slow down. Even these cosmic dynamos, these spinning titans that drag space-time itself around with them, eventually wind down. Their rotation slows, the ergosphere shrinks, and they return to a state of perfect, still silence. A non-spinning, or Schwarzschild black hole. Even the most dynamic objects in the universe eventually find rest. We cannot hear black holes in the traditional sense, for sound cannot travel through the vacuum of space. There is no medium for the waves to propagate, but NASA has taken data and given us a way to listen to the universe in a new way. They took pressure waves, ripples in the hot, thin gas from the Perseus galaxy cluster, waves that were sent out by its central, feeding black hole. These waves are literal sound waves, but they are far too low a frequency for the human ear to hear. about 57 octaves below middle C, but in 2022, NASA sonified them. They scaled the frequencies up by 57 and 58 octaves, bringing them into the range of human hearing. What resulted was a deep, haunting, multi-toned hum, a chord of pressure waves that had been traveling through space for hundreds of millions of years. It is a chord played on the very fabric of a galaxy cluster, a lullaby from the abyss, the closest we can come to hearing the voice of a black hole. Black holes may be responsible for some of the fastest moving stars in our galaxy, known as hypervelocity stars. These are stars moving so fast that they are unbound from the galaxy and will eventually fly off into intergalactic space. The leading theory is that they are the result of a gravitational slingshot. If a binary star system wanders too close to the supermassive black hole in the galactic center, the complex three-body gravitational interaction can fling one star away at incredible speed, over 1,000 kilometers per second, while the other is captured into a tight orbit around the black hole. The ejected star becomes a lonely, high-speed traveler, a runaway sent flying out of the galactic core on a one-way trip into the great, dark, intergalactic void. The black hole information paradox is one of the most profound and persistent puzzles in all of physics, a conflict between general relativity and quantum mechanics. Quantum mechanics states that information, the identity, state, and history of what fell in, can never be truly destroyed. But if matter carrying information falls into a black hole, and that black hole then completely evaporates via Hawking radiation, what happens to that information? Is it lost forever, violating quantum mechanics? Or is it somehow encoded in the Hawking radiation or preserved on the event horizon? This paradox has troubled physicists for decades and remains a gentle, unsolved mystery, a deep thorn in the side of theoretical physics, hinting at a deeper theory of quantum gravity yet to be discovered. A fascinating and hypothetical idea is that of primordial black holes. These would not be formed from dying stars, but from the extreme densities present in the very first moments after the Big Bang. If a region of the early universe was dense enough, it could have directly collapsed into a black hole. If they exist, and if they are abundant in a certain mass range, they could constitute a portion, or even all, of the mysterious dark matter that holds galaxies together with its gravity, but does not emit or interact with light. These tiny, ancient black holes could be drifting unseen through our galaxy right now, their collective gravity shaping the motion of stars. They are hypothetical ghosts, possible answers to one of cosmology's biggest questions. We are still searching for them. The temperature of a black hole, according to Hawking's calculations, is inversely related to its mass. The larger the black hole, the colder it is. A large stellar mass black hole is incredibly cold, just a few millionths of a degree above absolute zero. But a very small, low-mass primordial black hole would be intensely hot. And this leads to a strange and fascinating fate. As a black hole shrinks by emitting Hawking radiation, it gets hotter. As it gets hotter, it radiates energy faster, which makes it shrink faster and get hotter still. This is a runaway process, a positive feedback loop. The final moments of a small black hole's life would be a sudden, silent, and immense release of energy, a final quiet pop in the cosmos, a burst of gamma rays and particles, the last sigh of a dying dark star, the black hole's shadow, like the one photographed in M87, is not the event horizon itself. It is about 2.5 times larger. This is because the black hole's gravity is so strong that it bends the paths of light from the background accretion disk, wrapping it around the black hole and creating a shadow of absence that is larger than the true point of no return. The bright ring we see is light from the accretion disk being bent around the darkness from all sides, creating a perfect or nearly perfect circle. The ring is brighter on one side because the material in the disk is moving toward us on that side, and its light is Doppler boosted, making it appear brighter. It is a magnificent trick of the light, a gravitational illusion on a cosmic scale, a perfect demonstration of general relativity in action. There is no single center to the universe. But if we were to find the center of mass for our local group of galaxies, the Milky Way, Andromeda, the Triangulum Galaxy, and their dozens of satellite galaxies, it would lie in the empty space, the void between our galaxy and Andromeda. This precise point is dictated by the immense masses of the galaxies, masses which are dominated by their dark matter halos, but also significantly influenced by the supermassive black holes at their hearts, which contribute millions of solar masses each. Their silent gravity, though a tiny fraction of the total, helps steer the motion of entire galaxies. They are part of the cosmic calculus that determines how our local family of galaxies moves and will eventually merge. Black holes can, in a way, be used as natural telescopes. Their incredible gravity bends light from objects located directly behind them, an effect called gravitational lensing, predicted by Einstein. A perfectly aligned black hole could create a perfect Einstein ring, a brilliant, complete circle of distorted and magnified light from a distant galaxy or quasar far behind it. This natural lens can magnify the light of these distant objects, allowing us to see them in greater detail than we could otherwise. It is a natural telescope of immense power, provided by the gravity of the black hole itself. The concept of a white hole is a fascinating theoretical idea. It is imagined as the time reversal of a black hole. If a black hole is a place where things can only fall in and never escape, a white hole would be a place where things can only spew out and nothing can ever enter. While it is a mathematically valid solution to the equations of general relativity, no known physical process could create one, and we have certainly never observed one. Some speculative theories have suggested that the Big Bang itself could be viewed as a white hole, or that a black hole in our universe could be connected to a white hole in another. But for now, it remains a beautiful, peaceful, and purely mathematical thought, a cosmic fountain of creation, eternally pouring light and matter into the dark, a hypothetical source. Ultimately, the study of black holes teaches us about the fundamental nature of reality itself. They are natural laboratories for the most extreme physics imaginable, places where space is warped beyond recognition, time is stretched to its limits, and the quantum world of the very small meets the cosmic scale of the very large. In their silent, profound darkness, they hold the keys to understanding the deepest laws that govern our universe. From the very smallest particles to the largest structures in the cosmos, they challenge our assumptions, force us to invent new mathematics, and push the boundaries of human knowledge. They are the ultimate teachers, and their lesson is one of humility and wonder. As you drift closer and closer to sleep now, let go of the specifics. Let the concepts of singularities and event horizons and gravitational waves blur together into soft, comfortable. Imagine the gentle, immense pull of a black hole not as a force of destruction, but as a force of profound peace, a place where the noise and complexity of the universe are quieted, where all motion slows, where light itself slows down, rests, and is finally still. A place of ultimate calm and silence, a cosmic sanctuary of rest. You are safe, you are warm, you are resting here, in your bed, on a small, beautiful planet orbiting a gentle star. In the quiet suburbs of a spiral galaxy, the black holes of the universe are far, far away. Silent sentinels in the deep night, their immense gravity holding galaxies together in a gentle cosmic embrace. They are part of the beautiful, balanced, and peaceful machinery of the cosmos. They are not to be feared, but to be wondered at from a safe and comfortable distance. Remember this as you drift away. The atoms in your body, the calcium in your bones, the iron in your blood, the carbon in your cells, were forged in the hearts of stars that lived and died long ago. Some of those very stars may have ended their lives in the dramatic collapse that creates a black hole. In a very real, physical way, you are connected to these cosmic wonders. You are made of the same stuff, part of the same grand, quiet, and beautiful story of stellar life and death. You are stardust, contemplating the silence that created it. Tonight, as you sleep, know that black holes will continue their slow, silent dances across the cosmos. They will merge in silent, rippling embraces. They will slowly, patiently feed on wisps of gas. They will evaporate over timescales too vast for the human mind to grasp. And you can rest easy, wrapped in your blankets, knowing that you are part of a universe that is both beautifully mysterious and profoundly, deeply peaceful. A universe of immense energies and perfect silences. There is nothing more to do now, nothing more to think about. If you happen to still be awake, you can let go completely. Allow your breathing to become slow and steady. Let your heartbeat calm. Let the darkness behind your eyelids become as deep and peaceful as the event horizon of a sleeping black hole. Let your body feel heavy, supported, and calm. Let sleep pull you in as gently and inevitably as gravity. I hope you sleep deeply tonight and dream of quiet, drifting journeys among the stars. Good night.